Swayam Prabha. Digital India. Educated India.
Welcome to this course on transition metal organometallics in catalysis and biology. We have been talking about non-group 4 metal based olefin polymerization catalyst. This is indeed a very interesting area that we have been focusing upon, and to say the least, that this started actually the whole field of olefin polymerization catalysis actually originated from are non group 4 metal based phenomenon, and this is what is the famous nickel effect that led to identification of group 4 metal based transition metal complexes, which are extremely active for olefin catalysis, and then subsequent research in areas which are beyond group 4 transition metals, they eventually took place, and in that context we have spoken about the lanthanum transition metal complexes. Also we have spoken about iron, and then in the last lecture we had seen how palladium took the center stage. First nickel and then palladium. For nickel, the story has been that it has been like coming to a full circle, because it is the nickel effect which had indeed led to the start of these polymerization of olefins, and then later on it is the Bruchert who had developed catalyst which was sort of useful for olefin polymerization. So, let me just run it down. So, we started with nickel in so called nickel effect, led to titanium, Ziegler Natta, which led to zirconium as well as titanium metallocene catalyst. This was heterogeneous and these were homogeneous. That led to lanthanum metallocene, again homogeneous. Now, this is a non group 4 metal. Then we went to iron, and this was non CP ligand, and then finally from iron with Bruchert we went back to nickel, which was this famous nickel catalyst that of this type. The ligands which are used are or and they mainly are of this type. The catalyst represented are or bromides, now with nickel this could produce long chain linear polymer as well as oligomers depending on the substituents of the nickel, followed by the work by Bazan, which we had discussed about in the tandem catalysis, where they could produce a ethylene 1-butene copolymer using a single monomer. So, now there is another interesting discovery which sort of change the field in a dramatic way, is that when this metal when the metal bound to this ligand, is changed from nickel to palladium, then there is a startling discovery, and the startling discovery is that when this metal is palladium, then one can do polymerization of olefin with functional comonomers. So, this is really a very interesting discovery, because olefins with functional group sort of poisons the catalyst, and such kind of copolymerization with olefin with functional monomer absolutely was a real tough challenge at that point of time, and this was overcome by substituting nickel, which happily did ethylene polymerization or ethylene alpha olefin copolymerization with palladium, that sort of could carry out ethylene polymerization with polar functional monomers. So, this is a very interesting story. It was again developed by Bruckert in the JACS 1988 paper. The request the interested students to look this reference up. And the copolymerization was shown over here, olefin plus vinyl monomers, functionalized monomers in presence of the catalyst of this type. Palladium methyl OET plus and PAr 4 minus, a non coordinating anion in dichloromethane 1 to 6 bar pressure, 30 degree centigrade. So, almost a room temperature reaction could give this much wanted CH2X OR CH2Y CH2W CH3 CH2Z N. So, this is amorphous, highly branched product with polar ester groups, polar ester side groups. So, this is a very interesting discovery which could copolymerize, and that there is a polar functional side group now present on the polymer backbone. So, this was sort of the breakthrough first provided by Bruckert in being able to carry out polymerization of polar functional monomer with olefin. Subsequent that there were other groups like Grubbs and so on and so forth could report some other complexes, as well as Bazan report other complexes that could successfully carry out such polar polymerization. Now, moving on, there was another focus was on obtaining being able to actually polymerize ethylene and carbon monoxide CO copolymerization. It is important to note that C2H4 homopolymerization is possible. However, CO homopolymerization is not possible, and these would result, this polymerization would result in polyketones, which have very important polymer properties, are important for their polymeric properties. Now, for being able to carry out this ethylene CO copolymerization, the first report was given by Rapi in 1952, who sort of had observed that if one takes alpha olefins and carbon monoxide in presence of catalyst, then one could get a polyketone, poly 3 oxo trimethylene. In presence of a catalyst like K2 NiCN4 in some product. So, one could see its formation, and that was first reported by Rapi in 1952. The first breakthrough was, however, reported by Drent about more than 30 years later in 1996, when using a catalyst he could polymerize ethylene and CO using a phosphine based catalyst. In HOTS methanol 65 degree centigrade, 40 bar pressure, he could make polyketone molecular weight 200,000 Tm equals to 60 degree centigrade, and this is a thermoplastic material. So, the breakthrough actually in being able to make polyketone successfully in being able to polymerizing came much later in 1996 as a report from Drent. Now, there are two aspects to it. The first observation was, however, made by Rapi in 1952. Now, there are two aspects to it. One is that the alternating addition of CO as well as ethylene to give polyketone, and there were this polyketone polymer showed that it was really indeed a alternating polymer, where both the groups were inserting one after another, and that is what which was confusing, because though CO homopolymerization is not known, but ethylene homopolymerization is quite known. So, there were chances that one may see 2-3 ethylene insertion followed by 1 CO, but to everybody's surprise, what was found that the polymer really had 1:1 incorporation of ethylene and CO, which said that it is indeed an alternating insertion of CO and ethylene. Now, based on the catalyst and the proposed mechanism and doing the end group analysis of a polymer. So, actually this is a very powerful method of finding out the insight about the polymer mechanism is by looking at the end groups which are present in the polymer, and what they showed that there were 2 end groups, one is carbonyl compound, another is ester compounds, and the fact that the 2 end groups are provided obtained in nearly equal amounts, which sort of said that both the polymerization were happening in equal way. So, this is illustrated by this nice example of the mechanism shown over here. So, for example, the catalyst, which is in short is written by PP a palladium acetate, or maybe I will draw it nicely. This catalyst would give a catalyst precursor which is drawn by losing 2 acetate, the catalyst precursor. So, now there are 2 pathways, one I am showing in green. So, it can add CO to give PD CO 2 plus and that can take methanol, add methanol, giving out H plus and resulting in the compound PD PD CO plus. And then once this is formed, this can subsequently undergo various coordination insertion of ethylene and CO to give a polymer PD with the polymer with the end group being a ketone. So, alternating ester end group in polymer, whereas the other possibility it might as well be it first takes methanol and gives out H plus to give P PD OCH3 plus, and that can eliminate aldehyde CH2O, giving palladium hydride, which again can do CO ethylene polymer to give a polymer which has a ketone end group. So, alternating ketone end group. Now, this species again can react with CO to give the ester. So, now the glimpse of the mechanism can be obtained by the fact that one can get a alternating polymer with ketone end group, or one can get an alternating polymer with ester end group, depending on how in what sequence it reacts with the solvent, and this also throws insight as to mechanism of this polymerization reaction. And the chain propagation happens through alternating insertion step, as is shown over here. Giving CO. Now, this CO comes and enters over here to give the product which then binds to an olefin. Now, once the CO has inserted, the olefin would also insert over here, then the corresponding the inserted product would be now again to this another molecule of CO will come, which will come and insert over there to give the corresponding CO inserted product, and that subsequently will result in poly 3 oxo tri methylene polymer. So, these are polyketones. Now, what is interesting about here is the fact that both CO and ethylene, they are undergoing insertion alternatively. So, for example, here. So, it is sequential alternating insertion which is happening. Now, to sort of have an insight on this, one has to consider the following. For example, there are chances that instead of having this alternative insertion, there can be chances that double insertion of carbonyl can happen, two insertion of carbonyl. Now, double insertion of carbonyl is an uphill and impossible task, so that is discounted. Double insertion of CO is an uphill task and hence discounted. That means that CO homopolymerization does not happen and it is discounted and hence is not considered. So, then what is one left with is a double or homopolymerization of ethylene or alternating polymerization of ethylene and propylene. Now, homopolymerization of ethylene is energetically favored. So, has to be considered or taken into account, and finally, the mechanism of this has been elucidated by Brookhart, a very elegant example mechanistic study in 2000, which sort of explained provided evidence in favor of this alternative insertion of palladium. So, what Brookhart did was he showed that this catalyst is present in two forms. For example, this is the polymer chain where ethylene is coordinated. So, when that is formed, it has two possibilities. One is that it can insert to this, or the one maybe I illustrate this with the thing. One possibility will that this will undergo insertion, and what is the this is possibility number 1, and other possibility is that these coordinates may be replaced by a carbonyl, which is a more stronger binding. So, this is possibility number 2. So, if carbonyl displaces ethylene which is more fast, then and this is a very fast reaction, and K equilibrium is about 10 to the power 4 10,000 times faster, then it produces this palladium CO coordinated compound plus ethylene and this CO. And now then CO can insert into this olefinic bond. CO can insert into this olefinic bond to give the alternate CO polymerization. As is shown over here, and the other thing can be a double insertion, as we said that this possibility number 1 where this can insert into this, then the double inserted product can also be PD CO, this is PD plus. So, what we find over here is that 2 insertions of olefinic unit has happened. One is this, another is this. Now, this and this let us say is given by K1 dash. So, the ratio of K1 by K1 dash is approximately a 10 to the power 200. So, overall as let me summarize, as this is bigger, much greater than this, as well as this equilibrium constant is 10 to the power 4 times in favor of this. So, it is what we see is favored, the alternating insertion of ethylene with polyethylene is what is favored. So, with these we come to the end of the catalyst development story, the non group 4 the metals, and let me just summarize the overall findings of this work which has been discussed so far. So, there are actually 2 types of metals. First is the early transition metal. Early transition metal, and we had also this is how we started the story with, and then we had seen that the central metal atom for these early transition metals usually are titanium 4, zirconium 4, hafnium 4, lanthanum 3. Then the ligands which are used for this ligands in pre-catalyst usually had been Cp minus and halides, counter anion for these case the counter anion had been non coordinating, coordination geometry the coordination geometry is pseudo octahedral, active site is of this geometry and functional group tolerance and in this case absolutely none. And what we saw that as we evolved from early transition metal to something of late transition metal in the course of catalyst development, what was found that the metals which really did well are iron 2, then nickel 2 and palladium 2. Actually they sort of did the trick, whatever was complementary or challenge for these early transition metal, they were made by the late transition metal. The ligand used were diphos, these are non-CP type ligands, diamine or halide X minus type of ligand. Counter anion however is the same, weakly or non coordinating counter anion. In terms of active site is almost similar of what we had seen. Coordination geometry is probably I will write that first. Coordination geometry is pseudo square planar, mostly mostly square planar, and that is inconsistent with D8 configuration of nickel and palladium, and the active site is shown over here. And there is the vacant site, and functional group tolerance, yes, that is a big yes for late transition metals, that they are indeed functional group tolerant. So, here is the summary which brings out the comparison between the early transition metal and the late transition metal, and which sort of differentiates between the two is this functional group tolerance, and that sort of helps this late transition metal to carry out copolymerization of ethylene with polar functional monomers. So, with this we come to the conclusion of today's lecture, and hereby in this lecture we complete our discussion on the transition metals in catalysis aspect of this course, where we have seen a lot of important industrial large scale processes that are carried out by organometallic catalyst, right from rapid synthesis, metathesis, polymerization, so on and so forth. And then we move on to another very interesting aspect of organometallic chemistry, that is bioorganometallics or the applications of organometallic chemistry in biology. This aspect actually is still in the developmental stage, and we have few very exciting developments to talk about in the context of applications of organometallic chemistry when we meet next. And I once again thank you for being with me in this throughout this course. Particularly I enjoyed a lot talking about various important processes of organometallic chemistry, kind of showcasing the prowess of organometallic chemistry and the features of organometallic chemistry. And we move on to the other aspect of organometallic chemistry, particularly bioorganometallic chemistry. So, with this once again I thank you, and I look forward to take up the bioorganometallic chemistry in details when we meet next. Till then, goodbye and thank you.